Generated by AI human-assisted. Preamble. To identify advanced civilizations and their potential use of laser technology for communication, a 6-step process is proposed. Data collection on known or potential advanced civilizations, focusing on their technological advancement, communication strategies, and potential laser technology usage. Extracting relevant features from the data, such as advanced technology presence, evidence of interstellar travel or communication, and cultural or historical factors influencing communication strategies. Labeling civilizations as either likely or unlikely to use laser pulses or patterns for interstellar communication based on the extracted features. Training a machine learning model, such as a decision tree or support vector machine, to learn the relationship between the features and labels. Testing and evaluating the model on a separate dataset. Tuning parameters as necessary to improve accuracy. Deploying the trained model in a real-time system to analyze incoming data on potential advanced civilizations and predict their likelihood of using laser pulses or patterns for interstellar communication. To ensure accuracy and reliability, measures such as cross-referencing data, using multiple machine learning algorithms, and updating the system with new information should be taken. The system must also detect incorrect interference or noise in LiDAR signals using calibration, filtering, statistical analysis, and machine learning. Minimizing bias in the dataset and model can be achieved through stratified sampling, cross-validation, and pre-processing techniques. Detect LiDAR civilizations as it's faster and can be modeled after radio detection. Detecting intelligent life in the universe is a complex and challenging task, and it is an active area of research in the fields of astrobiology, astronomy, and SETI, search for extraterrestrial intelligence. LiDAR, light detection and ranging. Technology uses laser beams to measure distances and create 3D models of objects or environments. LiDAR has been used for various applications, such as autonomous vehicles, mapping, and archaeology. In the context of detecting intelligent life in the universe, LiDAR could potentially be used to detect signs of technology, such as radio or laser signals, that may indicate the presence of intelligent civilizations. However, the detection of such signals would require highly sensitive and specialized equipment, as well as extensive data analysis and signal processing. It would also require a deep understanding of the physics and mathematics behind signal detection and analysis. Therefore, creating a system that uses LiDAR technology to detect intelligent life in the universe would be a challenging task that would require the collaboration of experts from multiple fields, including astronomy, physics, engineering, and computer science. Yes, LiDAR-based detection of intelligent life in the universe could potentially be modeled after the SETI, search for extraterrestrial intelligence programs that use radio telescopes to search for signals from other civilizations. One advantage of LiDAR over radio detection is its faster speed, as LiDAR signals travel at the speed of light and can provide a more rapid response compared to radio signals, which can take years to travel across interstellar distances. To create a LiDAR-based system for detecting intelligent life, we would need to develop specialized LiDAR sensors capable of detecting and analyzing laser signals that may be emitted by advanced civilizations. We would also need to design advanced algorithms for processing and analyzing the data collected by the LiDAR sensors to distinguish between natural and artificial signals. In addition, we would need to identify suitable targets for the LiDAR search, such as nearby stars with planets in the habitable zone, and prioritize the search based on various factors, such as the age and spectral type of the star, and the potential habitability of the planet. Overall, the development of a LiDAR-based system for detecting intelligent life would require significant resources and expertise, but it could potentially complement existing SETI efforts and provide a new avenue for the search for extraterrestrial intelligence. LiDAR-based telescopes. LiDAR technology could be used to develop telescopes that are sensitive to laser signals, which could potentially be used by advanced civilizations for communication and propulsion. By searching for such signals, we could detect the presence of intelligent life. LiDAR-based interstellar probes. LiDAR technology could be used in interstellar probes to detect and analyze laser signals from other star systems. These probes could be sent to nearby stars to search for signs of intelligent life. LiDAR-based space-based observatories. LiDAR technology could be used in space-based observatories to search for laser signals or other signatures of advanced civilizations. These observatories could operate in orbit around planets or asteroids, or be placed at stable points in space. LiDAR-based detection of exoplanets. LiDAR technology could be used to search for exoplanets that may be habitable or have potential for life. By analyzing the reflected laser light from these planets, we could potentially detect the presence of atmospheres or other features that may indicate the presence of life. Can it be used to detect light pollution? LiDAR-based SETI experiments. LiDAR technology could be used in experiments that search for laser signals or other forms of extraterrestrial intelligence. These experiments could be carried out using ground-based or space-based equipment. LiDAR-based detection of artificial structures. LiDAR technology could be used to search for artificial structures on the surface of planets or moons, such as cities or other engineered features that could be indicative of intelligent life. LiDAR-based detection of exoplanets. LiDAR technology could be used to search for exoplanets that may be habitable or have potential for life. By analyzing the reflected laser light from these planets, we could potentially detect the presence of atmospheres or other features that may indicate the presence of life. LiDAR-based communication with extraterrestrial civilizations. LiDAR technology could potentially be used for interstellar communication with advanced civilizations. By sending and receiving laser signals, we could potentially establish communication and exchange information with extraterrestrial civilizations. LiDAR-based searches for Dyson spheres. LiDAR technology could be used to search for evidence of Dyson spheres or other megastructures that may be built by advanced civilizations. By analyzing the reflected laser light from these structures, we could potentially detect their presence. LiDAR-based detection of interstellar spacecraft. LiDAR technology could be used to search for interstellar spacecraft or probes that may have been sent by other civilizations. By analyzing the reflected laser light from these spacecraft, we could potentially detect their presence and study their characteristics. These, like search for anomalies of lasers. Yes, LiDAR technology can be used to detect light pollution. Light pollution refers to the excessive or misdirected artificial light that can affect natural habitats, astronomical observations, and human health. LiDAR sensors can be used to create 3D maps of urban areas and identify areas with excessive light pollution. By analyzing the reflected laser light from buildings and other structures, LiDAR sensors can detect the amount and direction of light emitted from different sources. This data can be used to create light pollution maps and identify areas where light pollution is most severe. Furthermore, LiDAR technology can be used to study the impact of light pollution on ecosystems, such as the disruption of migration patterns of birds and insects. By creating detailed maps of natural habitats and analyzing the light levels, LiDAR sensors can help to identify areas that may be affected by light pollution and inform conservation efforts. Overall, LiDAR technology provides a valuable tool for the study and mitigation of light pollution, which is a growing concern in many urban and natural environments. LiDAR-based systems for detecting laser pulses or patterns that may be used by advanced civilizations for interstellar communication. By analyzing the temporal and spectral characteristics of the laser signals, we may be able to distinguish between natural and artificial sources. Use of LiDAR sensors to detect and analyze the reflected laser light from space debris or other objects that may be associated with advanced civilizations, such as abandoned probes or spacecraft. LiDAR-based detection of artificial structures on the surface of planets or moons that may be indicative of advanced civilizations, such as large-scale infrastructure projects or terraforming efforts. Use of LiDAR sensors to study the absorption or emission spectra of exoplanets in search of atmospheric signatures that may be associated with life, such as oxygen or methane. LiDAR-based detection of anomalous light sources or patterns that may be indicative of intelligent life, such as bright flashes of light or repetitive sequences of pulses that cannot be explained by natural phenomena. https://youtube/adga4jh3awo can be watched to view laser technology and see how we could use the tech for space. Developing a system that can weigh the importance of different features and predict whether a signal or pattern is indicative of intelligent life requires the use of machine learning algorithms. Here's a general outline of how such a system could be developed. Data collection. Gather a large data set of LiDAR signals, including both natural and artificial sources, to train the machine learning algorithm. Feature extraction. Extract relevant features from the LiDAR signals, such as intensity, wavelength, temporal characteristics, and spectral characteristics. Labeling. Label each signal as either natural or artificial. and for the artificial signals, label them as either indicative of intelligent life or not. Model training. Train a machine learning model, such as a neural network or support vector machine, to learn the relationship between the features and the labels. Testing and evaluation. Evaluate the performance of the machine learning model on a separate test dataset, and tune the model's parameters as necessary to improve its accuracy. Deployment. Deploy the trained machine learning model in a real-time system that can analyze incoming LiDAR signals and predict whether they are indicative of intelligent life. The system can weigh the importance of each feature by assigning different weights to each feature in the machine learning algorithm, based on their importance towards predicting whether a signal is indicative of intelligent life or not. For example, the weight assigned to the feature of detecting laser pulses may be higher than the weight assigned to the feature of detecting light pollution, based on the percentage ratings we assigned earlier. Overall, developing a machine learning system that can weigh the importance of different features and predict whether a signal is indicative of intelligent life is a challenging task that requires expertise in LiDAR technology, data science, and machine learning. However, with the increasing availability of LiDAR sensors and the growing interest in the search for extraterrestrial intelligence, such systems may become more common in the future. What methods does the system use to filter out the effects of noise and interference in the absorption or emission spectra of exoplanets? And how does it ensure that these filters do not remove potentially important signals associated with life? How does the system identify the specific characteristics of artificial structures on the surface of planets or moons, such as size, shape, or composition? And how does it account for potential natural structures that may have similar features? What criteria does the system use to identify space debris or objects that are most likely to be associated with advanced civilizations, such as their trajectory, composition, or size? How does the system distinguish between anomalous light sources or patterns that may be indicative of intelligent life and those that are caused by natural phenomena, such as stellar flares or atmospheric disturbances? How does the system select the LiDAR signals to be included in the dataset? And what criteria are used to ensure that the dataset is representative of different types of signals and sources? What measures does the system use to ensure the accuracy of its light pollution detection, such as cross-referencing with other data sources or using machine learning algorithms to distinguish between natural and artificial sources of light? What factors are taken into consideration in determining which types of advanced civilizations are most likely to use laser pulses or patterns for interstellar communication, such as their level of technological advancement or communication strategies? How does the system detect and correct for different types of interference or noise in the LiDAR signals, such as atmospheric effects or instrument malfunctions? What techniques are used to minimize potential sources of bias in the dataset and the machine learning model, such as stratified sampling or cross-validation? How does the system balance the sensitivity and specificity of the machine learning model to ensure that it detects as many signals as possible while minimizing the risk of false positives or false negatives? What are the potential limitations of the LiDAR technology for detecting advanced civilizations in different types of environments, such as in dense atmospheres or on the surfaces of planets with varying topography? And how are they addressed by the system? 1. The system may use various methods to filter out the effects of noise and interference in the absorption or emission spectra of exoplanets, such as statistical methods, signal processing techniques, or machine learning algorithms. One approach may be to identify and remove specific frequencies or patterns that are known to be associated with noise or interference, while retaining the frequencies or patterns that are likely to be associated with life. The system may also use a combination of filtering methods, such as time domain and frequency domain filters, to remove different types of noise and interference. To ensure that these filters do not remove potentially important signals associated with life, the system may use a validation or verification process, such as cross-validation or blind testing. This process involves testing the performance of the filtering methods on a separate dataset that is not used in the training or development of the system. By evaluating the accuracy and sensitivity of the filtered data, the system can ensure that it is retaining the relevant information while removing the noise and interference. Additionally, the system may also use multiple filters or approaches to filtering to increase its confidence in the retained signals. 2. Pattern recognition algorithms. To identify potential structures based on their size, shape, and composition. For example, the system may look for structures that appear to be regular in shape or exhibit symmetry. which may be indicative of artificial structures. The system may use various methods to identify the specific characteristics of artificial structures on the surface of planets or moons. One approach may be to analyze LiDAR signals and use advanced image processing techniques, such as feature extraction or pattern recognition algorithms, to identify potential structures based on their size, shape, and composition. For example, the system may look for structures that appear to be regular in shape or exhibit symmetry, which may be indicative of artificial structures. To account for potential natural structures that may have similar features, the system may use additional criteria or context to differentiate between natural and artificial structures. For example, the system may compare the identified structures with known geological features or use contextual information, such as the location or age of the planetary surface, to determine whether the structures are likely to be natural or artificial. Additionally, the system may use machine learning algorithms that are trained on a large data set of known artificial and natural structures to improve the accuracy and specificity of its analysis. Overall, the system may use a combination of advanced image processing techniques, contextual information. Here are some additional examples of how the system may identify the specific characteristics of artificial structures on the surface of planets or moons and account for potential natural structures that may have similar features. The system may use LiDAR data to create high-resolution 3D models of planetary surfaces, which can be used to identify potential artificial structures based on their size, shape, and orientation. By analyzing the geometrical properties of these structures, such as their aspect ratio or symmetry, the system can distinguish between natural and artificial structures. The system may use multispectral LiDAR data, which captures LiDAR signals at multiple wavelengths, to analyze the composition of potential structures on the planetary surface. By identifying specific spectral signatures associated with artificial materials, such as metals or ceramics, the system can differentiate between natural and artificial structures. The system may use contextual information, such as the location and distribution of potential structures, to determine whether they are likely to be natural or artificial. For example, if a large number of structures are clustered together in a regular pattern, this may be indicative of an artificial structure, whereas if they are randomly distributed, they may be more likely to be natural. The system may use machine learning algorithms, such as support vector machines or decision trees, to classify potential structures as natural or artificial based on a combination of features and contextual information. By training the algorithms on a large data set of known natural and artificial structures, the system can improve its accuracy and reduce the potential for false positives or false negatives. Overall, the system may use a variety of advanced techniques, including 3D modeling, multispectral analysis, contextual information, and machine learning algorithms, to identify and differentiate between natural and artificial structures on the surface of planets or moons. 4. Statistical analysis. The system may use statistical methods to compare the characteristics of the anomalous light sources or patterns with known natural phenomena, such as the frequency, duration, and intensity of the signals. If the anomalous signals are outside the range of normal variability, this may indicate that they are more likely to be associated with intelligent life. Contextual information. The system may use contextual information, such as the location and timing of the signals, to determine whether they are more likely to be associated with natural or artificial sources. For example, if the signals are coming from a location where there is a known extraterrestrial civilization, this may increase the likelihood that they are associated with intelligent life. Pattern recognition. The system may use machine learning algorithms, such as neural networks or decision trees, to identify patterns in the anomalous light sources or patterns that are indicative of intelligent life. By training the algorithms on a large data set of known natural and artificial sources, the system can improve its accuracy and reduce the potential for false positives or false negatives. Collaboration with other observatories. The system may collaborate with other observatories or researchers to confirm the findings and rule out potential natural causes. For example, the system may coordinate with radio telescopes or other instruments to search for complementary signals that may be associated with intelligent life. Yes, analyzing our own frequency that we technologically emit can also be a valuable approach for distinguishing between anomalous signals that may be associated with intelligent life and those that are caused by natural phenomena. By analyzing the frequency and other characteristics of our own technological emissions, we can better understand the range of signals that may be associated with advanced civilizations and develop more accurate statistical models for detecting these signals. In addition, there are APIs and databases that provide information on known technological emissions from various sources, such as satellites, spacecraft, and communication devices. By integrating this information into the system, we can improve the accuracy and specificity of our analysis and reduce the potential for false positives or false negatives. Overall, combining our own technological emissions with known emissions from other sources can provide a more comprehensive and accurate understanding of the range of signals that may be associated with advanced civilizations, and improve our ability to distinguish between anomalous signals that are likely caused by natural phenomena and those that may be associated with intelligent life. There are many frequencies that we technologically emit, including those used for radio and television broadcasting, satellite communications, cellular phones, Wi-Fi, radar, and GPS signals. These frequencies range from a few kilohertz to several gigahertz and can be detected by sensitive instruments such as radio telescopes or LiDAR sensors. In terms of searching for signals from advanced civilizations, it is difficult to predict which frequencies they may use. However, some scientists have suggested that advanced civilizations may use frequencies in the microwave or optical range, as these frequencies are less subject to interference from cosmic background radiation and can be more easily focused and directed over long distances. Overall, the search for signals from advanced civilizations requires a wide range of frequencies to be monitored and analyzed, and it is important to remain open to the possibility of unexpected or unconventional frequencies being used. By combining a thorough understanding of our own technological emissions with a comprehensive search for signals from advanced civilizations, we can improve our chances of detecting potentially life-changing signals. The system needs a large and diverse data set of LiDAR signals to train the machine learning algorithm and to evaluate the performance of the system. The selection of LiDAR signals for the dataset is a critical step, and must be done carefully to ensure that the dataset is representative of different types of signals and sources. One approach to selecting the LiDAR signals is to gather data from a variety of sources, such as satellites, ground-based telescopes, and airborne LiDAR sensors, to ensure that the dataset captures a wide range of signals and sources. Additionally, the system may use targeted observations of specific sources, such as exoplanets or potential extraterrestrial structures, to ensure that the dataset includes relevant signals. To ensure that the dataset is representative of different types of signals, the system may use stratified sampling methods that aim to balance the proportion of different types of signals in the dataset. For example, the system may aim to include a certain percentage of signals that are known to be associated with natural phenomena, such as stellar flares or atmospheric disturbances, as well as signals that are potentially indicative of intelligent life, such as laser pulses or anomalous light patterns. Finally, the system may use quality control measures to ensure that the LiDAR signals are of sufficient quality and reliability for use in the dataset. This may include filtering out signals that are contaminated by noise or interference, or that have other technical issues that may affect their usefulness for training the machine learning algorithm. Overall, selecting the LiDAR signals for the dataset is a critical step in developing an effective system for detecting advanced civilizations, and requires careful consideration of the different types of signals and sources that may be relevant. By using a diverse and representative dataset, the system can train the machine learning algorithm to accurately distinguish between natural phenomena and signals that may be indicative of intelligent life. To ensure the accuracy of its light pollution detection, the system may use a combination of measures, such as cross-referencing with other data sources and using machine learning algorithms to distinguish between natural and artificial sources of light. Cross-referencing with other data sources can help to verify the accuracy of the light pollution maps generated by the LiDAR sensors. For example, the system may compare the LiDAR data with satellite imagery or ground-based observations to identify areas of high light pollution and confirm the accuracy of the maps. Additionally, machine learning algorithms can be trained on a large data set of known natural and artificial light sources to improve the accuracy of the system in distinguishing between these sources. For example, the system may use neural networks or support vector machines to analyze the intensity, wavelength, and other features of the light signals and determine whether they are likely to be natural or artificial. Furthermore, the system may use contextual information, such as the location and time of the observations, to identify potential sources of artificial light. For example, if the LiDAR signals indicate a high concentration of light in a particular location at a specific time, this may indicate the presence of a city or other urban area. Overall, by using a combination of cross-referencing with other data sources and machine learning algorithms, the system can improve the accuracy of its light pollution detection and provide more reliable information about the extent and sources of light pollution in different environments. Determining which types of advanced civilizations are most likely to use laser pulses or patterns for interstellar communication involves considering various factors, such as their level of technological advancement and communication strategies. One key factor is the level of technological advancement of the civilization. Advanced civilizations that are capable of interstellar travel or communication may be more likely to use laser pulses or patterns for communication due to the advantages of laser technology, such as its speed and accuracy. Another factor is the communication strategy of the civilization. Some civilizations may have a preference for using laser pulses or patterns as a means of communication, based on cultural or historical reasons. Additionally, some civilizations may use different communication strategies for different purposes, such as using radio waves for long-distance communication and laser pulses for short-range or high-precision communication. The system may also consider the potential benefits and drawbacks of using laser pulses or patterns for communication, such as their susceptibility to interference and the level of energy required to generate the signals. Overall, determining which types of advanced civilizations are most likely to use laser pulses or patterns for interstellar communication requires a comprehensive understanding of their technological capabilities and communication strategies, as well as an assessment of the advantages and disadvantages of different communication methods in the context of interstellar travel and communication. Designing a system to determine which types of advanced civilizations are most likely to use laser pulses or patterns for interstellar communication would involve the following steps. Data collection. Gather data on known or potential advanced civilizations, including information on their level of technological advancement, communication strategies, and potential use of laser technology for communication. Feature extraction. Extract relevant features from the data, such as the presence of advanced technology, evidence of interstellar travel or communication, and cultural or historical factors that may influence communication strategies. Labeling. Label each civilization as either likely or unlikely to use laser pulses or patterns for interstellar communication, based on the extracted features. Model training. Train a machine learning model, such as a decision tree or support vector machine, to learn the relationship between the features and the labels. Testing and evaluation. Evaluate the performance of the machine learning model on a separate test dataset, and tune the model's parameters as necessary to improve its accuracy. Deployment. Deploy the trained machine